So in calculating these limits, we can look at several things. We can look at the graph. We can look at a table. Now our table, as we approach from the left and we approach from the right towards our limit of x equals 3, our table is going to -2. The graph, when we looked at the graph and trace around on the graph is also approaching, let's see. The graph is also approaching -2. As you come in from the left or as you come in from the right, you're getting closer and closer to that value. But if you are actually asked to prove it, sometimes on an exam I'll literally write graphs don't constitute a proof, or tables don't constitute a proof. This is what I'd be looking for. I'd be looking for you to take and play around with the numerator. What can I do in the numerator that might be helpful? Factor it. So that's going to equal the limit as x approaches 3 of x minus 3 times x minus 5, x minus 3. Notice you got this factor that's common to both the numerator and denominator, that x minus 3. That x minus 3 in the denominator is the reason that this thing is undefined at x equals 3. That's why you're getting a whole. But other than that point at x equals 3, this is pretty well defined. In fact, this is equal to this as long as you're staying away from exactly x equals 3. So in terms of the limit, which is what happens when you get arbitrarily close to something, we could say that, oh, well, that's equal to the limit as x approaches 3 of x minus 5. Now, there's a wonderful little theorem that I mentioned last time. If you have a nice continuous function and you're trying to evaluate the limit, you can just plug in the limit. All right? So right here, there's nothing that stops us from plugging in the limit. Up above, you would end up with 0 over 0. If you end up with 0 over 0, that's telling you got to do a little bit more work. So 3 minus 5 is your -2. And we saw that a total of 3 different ways. We proved it algebraically, we saw it with the table, and we saw it with the graph. So all 3 of those things should point in the same direction. That's the big message I'm trying to get across here today. And the other day. All right. Comments on example C?
So that's how you would want us to write it out on the test to show our work?
Yep.
Okay.
If I ask you to actually prove it, then this is what I'm going to be looking for. Now, at the end of this section today, we're going to go over 4 more examples of this kind of algebraic proof that, you know, each highlight different tricks, things that you're going to need in the homework and questions you might need to be answering on an exam. But let's move on to kind of a nice user-friendly part of this. One of the nice things about limits, and it sometimes happens, it sometimes doesn't, in mathematics, that things are what you would want them to be. Now, they're not always going to be that way. For instance, you know, I ran into this in my algebra class the other day. Square root of x squared plus 4 does not equal x plus 2. Sorry. It'd be nice if that doesn't. Don't give me a look of surprise. It'd be nice if that worked that way, but it doesn't. But as far as limits are concerned, limits do work kind of like what you would expect. So for instance, in example A here, I've got the limit as x approaches 2 of f of x plus g of x. Okay. Well, the nice thing is that I can rewrite that as the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. So I can split that up. And that's nice. Now, being able to split that up makes our life a little bit easier. So to find those limits, we have to look at the graphs here. Let's take a look at the graph of f. What's the limit as x approaches 2 of f of x? I got a -1 from Ethan. Do we agree, Harley? All right, good. So that's going to be -1. And someone else. Iris, how about limit as x approaches 2 of g?
2.
Yeah, 2. Now, interestingly enough, is f of x defined at x equal 2? Is there Can I find f of 2? No, it's a hole there in that graph. So it's not defined, but that doesn't prevent the limit from existing. -1 plus 2 gives me 1. So the limit here is 1. Great. Now I'm not going to try and squeeze the rest of these on here, but let's take a look at B. We want to take a look at the limit as x approaches 0 of f of x minus g of x. And here again, your intuition is a correct guide, that it feels like you can kind of distribute this limit. So that would be the limit as x approaches 0 of f of x minus limit as x approaches 0 of g of x. All right, so Jameson, maybe you can give me the limit as x approaches 0 of f of x, and Nashaya, maybe you can do the one for g of x, whenever you're ready.
For f of x, it was at 2.
Yeah, f of x from the left and from the right, you're getting close to 2. Nashaya? As x approaches 0 of g of x, what's happening? Or does that one not exist?
Does that one not exist?
Yeah, the second one doesn't exist, right? Because the limit from the right is going to 1. The limit from the left is going to 3. So it does not exist. And if that one doesn't exist, the whole thing does not exist. Yay, done. But the point here is that limits kind of behave in a nice friendly way in terms of being able to add or subtract them. Why don't you try example C? And thank you, Mashaya and Jameson. So, yeah, that's a multiplication. This time as x approaches -1 of f of x times g of x. What's your gut feeling telling you about this product? What do you think we're going to do? Yeah, you're going to multiply the limits. So it's going to be the limit as x approaches -1 of f of x times the limit as x approaches -1 of g of x. So again, we want to keep an eye on these functions. Take a look at both those limits. So Aiden and Pahana, whenever you're ready, Aiden for f of x. As x approaches -1, what's this limit getting close to?
I'm not sure if that's, is that a dot?
There's a dot up here, and there's a hollow dot down here. But does it?
On like what how that works with the,
Okay, so, but the limit is what's happening to the function as you get close to this point, right? So does it matter if I have a dot up here or if it's down here?
that would just be the y. That would just be a value that's existing.
Yeah, exactly. So as you approach from the left and as you approach from the right, what's
Looks like -1.
positive
Sorry,
1?
it looks like 1.
Yeah, there you go. So positive 1 times, and let's take a look at g of x. Now g of x happens to be nice and continuous. Pahana, what's the limit there? As x approaches -1 for g of x. So as you get close to -1 from the left and close to -1 from the right, where's that limit going to? 2, good. And 1 times 2 gives you 2. Nothing really dramatic there. Let's finish up a couple more of these. So this one does not exist. And this one was a 2. Limit of a quotient. What do you think you're going to do with that one?
Divide it.
Yeah, divide them. Limit of a quotient is the quotient of the limits. A little bit of a tongue twister there almost. So the limit as x approaches 3 of f of x over g of x. Well, we're going to rewrite that as the limit as x approaches 3 of f of x divided by the limit as x approaches 3 of g of x. And Let's do one or two more while we're doing this one. Let's see. E is kind of interesting. Limit as x approaches 2 of x squared times f of x. That's kind of a clever one. I'll let you think on that one. And let's go back and look at the graphs. If you're watching this at home, you might want to pause things and see if you can't figure out those two limits. So that would be these two here. Well, the first one, x approaches 3, second one, x approaches 2. You can borrow. So let's look at these together. Let's start out with the limit as x approaches 3 of f of x. So as we get closer and closer to 3, what's f getting close to?
1.
Yeah, f's getting close to 1. And if we get closer and closer to 3 over here, what's happening there? What's f? Oh, what's g of x getting close to? 0. So we end up with 3 over 0. That's kind of a problem, isn't it? 3 over 0 is pretty undefined. Undefined. Isn't it?
1.
1 divided by 0.
That's what I
Oh,
Or
my bad. 1 divided by 0. Yeah, 1 divided by 0. But it's still a problem either way, right? It's undefined, so that's kind of a bummer. You needed a little bit of cleverness to do this one. What's the key step in doing this one? Did anyone figure that one out?
do you have to square root?
No, it's not a square root. It's kind of like what we did with example C. We're going to split that one up into the limit as x approaches 2 of x squared times the limit as x approaches 2 of f of x. Now, the nice thing is that this is a nice, smooth, continuous function. There's no holes in it. There's nothing crazy that's going to go on in it. So what's the trick to try and evaluate the limit for this one? We don't have a graph, but do we need a graph? Just plug it in. Yeah, awesome. Thanks, James. So plug it in. It's going to be 2 squared. And then the limit as x approaches 2 of f of x. Let's see, approaches 2. I'm getting -1. From the right and from the left, you're going towards -1. So 2 times -1. Overall, you should get -4 there. Okay. Nice. Nice. The last one's a little bit different. And kind of like this one, so let's finish this up. We've got f of -1 and the limit as x approaches -1 of g of x. So, okay. Let's see, there's -4, undefined. Let's start with f of -1. Well, it's a hollow dot, but take a look a little farther north on the graph. Harley?
3.
Yeah. So f of -1 is actually defined up here it's not a continuous function, but it is defined. So it's 3. And the limit as x approaches -1 of g of x. John? 2. Nice. So as you approach from the right, as you approach from the left, you're getting closer and closer to that point. So overall, an answer of 5. Okay. Are we okay with example D? All right. So some nice user-friendly things that we can do when we're trying to evaluate limits. I would keep them in mind. I mean, they're pretty well-behaved operations in terms of mathematics. So, okay. Move on down to E. Example E. We're going to look at this graph a couple different ways. We're going to look at it with a table, we're going to look at it graphically, and we're going to try and calculate its exact limit. So the exact limit, by that I mean algebraically, kind of like what we did with example C here. So let's start out by plugging this into our calculators and maybe looking at it graphically, maybe looking at it with a table or something. Let me plug that in. Let's get rid of these. So, does it like that trick of the alpha key, numerator denominator? Let's do that one again. So we'll hit the alpha key, then the y equals key. That gives you a choice to write a straight up and down fraction. So let's do that. In the numerator, I want x. In the denominator, it's the square root of 1 plus 3x. And then you've got to hit the right arrow to get outside of the radical before you subtract your 1. So minus 1. Looking good. Let me clear out these. So you can kind of follow along my keystrokes down here if you need to. If you want to see what I've done. We've got to set up our window.
Do you want to do the decimal thing?
I don't think it's going to matter because I think we'll probably get...
Square root.
Yeah, we're probably going to get ugly enough numbers that we don't have to worry about it. But it's not a bad idea to put the decimal thing here on the off chance that you do get a decimal or a fraction. So let me hit the math key and then the second one. That way I'm guaranteed I get a decimal in my table. But let's start with the graph. And if you're unsure, it's like, well, what do I set my window to? There's a nice clue that you have. What's your clue as to where to set the window? I was thinking of something a little more basic. You've already got a graph, right?
Oh.
You can just mimic what we have here. I mean, there's no reason to think too hard. So let's go from, say, -1 to 4 on the x-axis, and, I don't know, -0.5 to 2 on the y-axis. So -1 to 4 on the x-axis. I would hit zoom 0, but you know I don't want to leave it up to chance. I actually want the graph that is pretty close to what we have on our sheet. Now, do you know what x scale and y scale do? You know what those are?
The little dash.
That tells you where all the tick marks are. So for instance, in this graph, x scale is 2 because you have tick marks every 2 spaces. So just to try and help you understand what that is, I'll do the same thing here. I'll put x mark or x scale equal to 2, but on the y-axis, let me put it as 0.5, just to show you a little bit of the difference there. So I should see like 4 or so tick marks on the y-axis, but only a couple on the x-axis. All right, let's take a look at the graph. And bam. All right, well, let's see. It's asking us what's the limit of this graph as x approaches 0. Well, we can take a look at that. It looks like it's around, I don't know. Well, keep in mind that that's a 0.5. This is 1. 1.5 and 2, so maybe 0.66 something. Yeah, sounds about right. But let's hit the trace key. and zoom in on things that way. And I want to get closer and closer to 0. This time I'm coming from the right. And the y value is getting close to 0.66 maybe. If I'm to the left, again I'm getting close to some value around 0.66, 0.67. So, okay. But those are kind of limiting. Let's see if we can do a little bit better with the table function. So let's delete all these values here. What would be a good sequence of points that help me figure out that limit?
0.1, 0.01, 0.001.
Awesome. Thank you, James. 0.1, 0.01, 0.001. That's coming in from the right. Now, to get full credit on your exam, what else do we have to do?
The other side.
You have to come in from the left. So negative 0.001, negative 0.01, negative 0.1, etc. Now, I do it symmetrically. It's just aesthetically pleasing to me, but you don't have to do it symmetrically. You could just do it in whatever order that makes sense to you. But there you go. You're getting closer and closer to 0.666. In fact, we can throw in another one just to double check that, 0.0001. And you're getting pretty close to 0.66666. Let's cursor on top of that, and yeah, you get 0.6667. So getting close to a number. What does that seem to suggest to you? What number does it feel like it's getting close to? If you had to guess. 2/3, yeah, 0.666666. Now, what if I actually asked you to calculate this thing directly? That's going to be a little bit more work. So let's see if we can't do that. Let's see. Example E. Let me give you a little reminder. And part of the reason that I don't really spend time on the early chapters is because I give you these reminders kind of just in time. Things that you need to know just when you need to know them. And the reminder is pretty simple. That is A minus B times A plus B. Can anyone, without foiling that out in their head, tell me what you're going to get when you multiply those two together? Somebody's whispering it. A squared minus B squared. That's a really cool little trick here. Keep that one in mind. We're going to use that perhaps a couple times today. So let's look at our limit as x approaches 0 of x over the square root of 1 plus 3x minus 1. Okay, looking good there. But let's see. Well, the first thing to always try is to plug in the limit. So try plugging in the limit. What do you get when you plug in the limit? Well, in the numerator you get 0. What if you plugged in a 0 into the denominator part of the function? What am I going to get?
Isn't it 0?
It's 0 again, right? 0 over 0 is telling you you've got to do some more work. It's not ready to evaluate this limit. So, I mean, this is undefined as it is. So we got to do a little bit more work. So, try something different. Well, keep in mind, I just gave you a little bit of a hint right there. All right, that was our just-in-time hint. Now, in working with limits, you can't like multiply both sides of an equation or square both sides of an equation because there is no both sides. You just have the limit. So I can, however, go back to one of the most tried and true tricks in mathematics, and that is multiply by 1. The question is, what form of 1 am I going to choose? Well, I'm going to look at this as being kind of an A minus B. What would be the A plus B to that A minus B? square root of 1 plus 3x plus 1. And then square root of 1 plus 3x plus 1 again.
Oh, you're turning it into that equation?
Yeah, I'm exactly using this idea up here that when I multiply these two things together, in other contexts I'll call them conjugates, but I'm going to get the difference of squares. In fact, this is important. You want to save yourself some time? Anyone interested in saving themselves some time on doing this? Yeah? Okay, a couple people? All right, that's good. I'm glad you didn't call my bluff because I was going to tell you anyways. We're going to take a look at the limit as x approaches 0. Now, I'm going to leave this factored in the numerator because I kind of anticipate some cancellation. But in the denominator, let's keep an eye on things. I've got, this is my A, and this is my B. A and B. I'm going to get an A squared minus B squared. So what's A squared going to look like? Well, square root of 1 plus 3x squared minus 1 squared. That's a lot easier than foiling this out. You don't have to go first, outside, inside, last. You just know that it's going to end up like this. So we're jumping to the happy ending. That's a nice little trick there. How does this simplify? No one can simplify that one for me? Yeah, 1 plus 3x minus 1.
Wouldn't it be plus 1 since
No, it's going to be minus 1. Because you have a minus times a plus. Yeah, you'll end up with a difference of squares. So, but what happens further? I can further simplify this, right? Cancel the ones. X and square root of 1 plus 3x plus 1 over 3x. If you tried plugging in the limit now, it still wouldn't work. Because you'd have a 0 times whatever in the numerator and 3 times 0 in the denominator. You'd have 0 over 0. But we're so close.
factor out the x's?
Yeah, let's cancel out the x's, right? And that's the whole point of what we did, is being able to get rid of the problem child in the denominator, which is that 0 that we get. So now what do we have? Well, now it's the limit as x approaches 0 of square root of 1 plus 3x plus 1 over 3.
Just for this example, couldn't we remove the x and 3x because we know it's going to be 0?
Well, I'm not sure what you mean by remove it, but there is something that makes this problem really easy at this point.
Keep plugging the limit out?
Yes, and just plug in the limit.
Oh, okay.
So, I mean, it kind of removes the 3x. You know, maybe that's what you're hinting at. Yeah, but plug in the limit. I mean, always keep that in mind, that one of the things you want to try in working on these things is plug in the limit. So I get the square root of 1 plus 1 over 3. I'd really appreciate that at this level you simplify the square root of 1 for me. 2/3, which is what our table was saying, which is what our graph was saying. Both of those are pointing at the direction, and there it is. Nice, 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 nice. Okay, so a good little trick on that one. Keep that one around. Comments or thoughts on example E there? Good on that one? Yes, sir.
The answer, like writing that on an exam, would you just want us to mark out like A, B, C, and then box them or something?
You mean like I did here?
Oh, no, I mean like, because the example, like the question is graphically A with a table B.
Oh, yeah, I'd have room for you to
Oh,
write
okay.
those things. Yeah, yeah. All right. Anything else on this one?
The last line of the screen, like one more time. Thank you.
Sure. Yeah. Okay. Let's look at example F. Now, example F is going to require you to be a little bit thoughtful on your calculator. And we're going to do this one with a table and or graphically. So it's going to require us to put in this function 2x plus 14 over the absolute value of x plus 7. Does anyone know where to find the absolute value on your graphing calculator? Yeah, it's in the math menu. And I think you got a cursor to the right to get to numbers. And it should be like the first or second option.
Yeah.
But I'll get there in a second. Let's see, 2. All right. So what I'm going to do is I'm going to start by putting this into my graphing calculator. And let's clear out a bunch of stuff here. I'm going to hit the alpha key and then the y equals key. Now, if you don't have a TI-84, this won't be available to you. If you have an older TI-83, then yeah, bummer. But it is available to me here, so I'm going to use it. 2x plus 14. Cursor down to the denominator. Hit the math key. This time go over to numbers. And the first thing you'll see there is the absolute value. Now when you press it on the TI-84, it's actually going to give you that absolute value symbol. So the absolute value of x plus 7. And they're asking us for the limit as x approaches -7. So you want to look at this with the graph or with the table first?
Right.
Graph? All right. Where should I set my window?
-6 and -8.
Nice. We want to put -7 at the center of things. So we're going to put it, a window of -8 to -6. That puts -7 at the center of things. Now in terms of the y direction, if you don't know what's going to happen with the y direction, you can hit zoom 0, and that'll clean things up for you. Let me help out with the y direction just in the interest of time. Let's go from -2.5 to +2.5. I'm going to go through and set y scale equal to 1. And let's hit the graph key with those settings. Any predictions? Is this limit going to exist? Yeah, not looking too good. Why not? What's wrong with this limit? Lucas?
Approaching from the left is -2, approaching from the right is +2.
Yeah, the limit from the left and the limit from the right are different. So, yeah, this one's not going to exist. Now, if you needed to fill things in with a table, then try and plug in some values that suggest the limit from the left and the limit from the right. Now, I've already got some values plugged in here for you that kind of go through that same motion, but I think we're going to end up with pretty repetitive values here. So it should be pretty easy. Let's type in -7.3, -7.2, etc. And what you're seeing is what is reflected in the graph is that it's just always, always, always -2 when you're approaching from the left and +2 when you're approaching from the right. And it's actually undefined at x equal -7. So, but that doesn't matter in terms of the limit. So the limit from the left as x approaches -7 from the left, 2x plus 14 over absolute value of x plus 7 equals -2, and that's not equal to the limit as x approaches -7 from the right. So this limit does not exist. Beautiful. Beautiful. So I got a little challenge for you. For example, G. What I want you to do is stay in between these two lines. So let me highlight these here. Stay in between this line and this line. Draw a function without lifting your pen from the paper that goes from here over to here. So it can be anything you want. Just draw some kind of function up and down, left and right, or just straight through, whatever. But get from the left-hand side of the graph to the right-hand side of the graph, any way you choose, staying between these two lines all the way. So anything you want. Just draw something that snakes its way from the left side of the graph to the right side of the graph. So for myself, something like that. Whatever, doesn't matter. I'm going to make a prediction about all your graphs. So if I call this f of x, my prediction for your graph and all the graphs is that the limit as x approaches 0 of f of x is 0. It has to be, right? Because why? Because you're stuck between these two curves, right? And these two curves, or these two lines, have a limit at 0. So what's happening? You're getting squeezed into that limit, right? No matter what you did in going from the left-hand side of the graph to the right-hand side of the graph, you had to pass through this point, didn't you? So, I mean, not a big shocker there. That's literally called the squeeze theorem. It says if you have two functions that bound something and they go to a limit, then that middle function has to go to that same limit. So that's what's going on with example G. You've got these two functions, so this one and this one, that are bounding some f of x. We don't know what f of x is. F of x is kind of like, this is going to be kind of like what we just did with this one. F of x has to squeeze in between here like that. So its limit at x equals 0 has to be the same thing, or excuse me, at x equals 2 has to be the same thing as this limit and this limit. So let's calculate those two limits. All right. So let's see. Example G. We've got 2x minus 2 is less than or equal to f of x less than or equal to x squared minus 2x plus 2. If I want to know the limit as x approaches 2, then it's enough to calculate the limit as x approaches 2. I think how I want to write this. Well, let's just do the whole thing. Of 2x minus 2 less than or equal to f of x less than or equal to x squared minus 2x plus 2. So that's going to mean the limit as x approaches 2 of 2x minus 2 is less than or equal to the limit as x approaches 2 of f of x, and that's going to be between this one and this one, these two limits. Okay, pretty cool, pretty cool. Alex, any suggestions? I need to calculate this limit. Any suggestions as to an easy way I can find that limit? Yeah.
Break it up into what sections?
All right, we could split this up as a limit as x approaches 2x minus a limit as x approaches 2. But is there some way that's a little easier?
Plug it in.
Plug it in. So as long as plugging it in works, you're great. As long as it doesn't, ask you to divide by 0 or create a 0 over 0, plugging it in works. So if I plug it in here, what do I end up with? Try again.
Oh, 2.
2. Yeah, 0 rounded up to 2 is 2. All right, so yeah, the limit there is 2. Now we don't know what this one is, but we do know it's between these two. How about over here? What are we going to do without that limit? Emma, suggestions? Oops, this should be a 2. What's the first thing we always try when we try and evaluate a limit? Try plugging it in. Is there anything that prevents us from plugging it in? Do we end up with a square root of a negative number or something over 0? No. So 4 minus 4 is 0, plus 2 is 2. So we calculated both these limits. We got 2 each time. Since this one is less than or equal to f of x and this one's f of x is less than or equal to this, what does the limit of f of x have to be? 2. So therefore, by the squeeze theorem, limit as x approaches 2 of f of x equals 2. Nice. All right.
If those greater than or equal to, or less than or equal to sign, if it wasn't equal to, that would be something else.
Yeah, if I didn't have the less than or equal to on both of these, then it wouldn't be telling me what I really want, typically. So yeah, it has to be a less than or equal to. Yep. Ethan, good? Okay. Let's get down to the last few, the biggies. These require a little bit of thought. And kind of another just-in-time little gem that I'm going to throw your way is a really cool thing. It's called Pascal's triangle. So these are all part of the last set of examples. I don't think I have it labeled. Call it example H, maybe, just for giggles. I'll label that one here, example H. Well, let's start out with this one. Before I start out with this one, let me save you a lot of work, at least hopefully save you a lot of work. Have you ever seen Pascal's triangle? 1, 1, 1, 1, 2, 1. No? It's for finding the coefficients of expanding a plus b first to the 0, a plus b to the first power, a plus b to the second power. Anything to the first power is just 1. A plus b to the first power is just a plus b. But can anyone square this out in their head? What do you get when you square a plus b?
A squared plus AB plus B squared.
Close, plus 2ab
Oh, 2AB.
plus b squared. Now take a look at the coefficients here. These coefficients here match these coefficients here. So kind of nice. Now why do I care? Well, because in this problem, you have a choice of how you expand a plus b cubed. Now, in order to find the successive rows here in Pascal's triangle, what you're going to do is you're going to start out with a 1 and a 1 on either end. And to get the numbers in between, you're going to add the two numbers above. So for instance, 1 and 1 gave me 2. What number is going to go here? 3. And then 3 again. And that's going to be the coefficients for a cubed plus 3a squared b plus 3ab squared plus b cubed. Nice. So expanding it out is going to be a lot easier using Pascal's triangle, or you could do a plus b times a plus b times a plus b and multiply them all out and collect like terms and spend about a week doing this thing as opposed to, you know, a few seconds. So it's a nice little trick. I can probably direct you to section 12.6 of my college algebra, my math 1540 videos. We'll talk about Pascal's triangle a little bit and how to expand these things. So if you want some more help there, there's tons of videos there. But we're going to use that for this one. The limit as h approaches 0 of 6 plus h cubed minus 216 over h. Laura, what's a good place to start? In any limit problem, not just this one.
Plug it in.
Well done. Plug it in. So we plug it in, and let's just do a little mental calculation here. 6 plus 0 is 6. 6 cubed is 216. 216 minus 216 is 0 over 0. Always, always, always try plugging it in, though. So Laura was right. Try plugging it in. It doesn't work. This says we need more work. Need to do more work. All right. Well, what can we do? Just like our other problem, I gave you this just in time. We're going to expand this using this idea. So it's going to be the limit as h approaches 0. Let me give myself some room here. I want a cubed. So it's going to be, this is going to be my a. That's my b. So a cubed is going to be 6 cubed plus 3 times 6 squared times h. 3 times 6 squared times h. 3 times 6 times h squared plus h cubed minus 216 over h. Now nothing much has really changed. If you tried plugging in a 0, you'd still end up with 0 over 0. So, you know, we're not going to go there. Let's try and clean this up a little bit. That's going to be the limit as h approaches 0 of 216. That's going to be what? 36 times 3 is going to be 108. H plus 18 h squared plus h cubed minus 216 over h. But I think we got to a place that we can actually do something now. What can we do that might be helpful? Christian?
Divide by h. Cancel out h's.
Let's cancel out the, not the h, the 216. But keep an eye on that h though, because you were heading in the right direction. Limit as h approaches 0 of 108h plus 18h squared plus h cubed over h. And Christian, I think you're noticing something about all these terms in the numerator. We're ready for it now. What do these all have in common? Yeah, they all have an h. We're going to factor that out. 108 plus 18h plus h squared over h. I still can't plug in h equals 0, at least until I do one more step.
Cancel out the h's.
Cancel out the h's. Yeah. Let's get rid of the h's. And that's going to be the limit as h approaches 0 of 108 plus 18h plus h squared. Whew. Wow. Man, I envy you guys. It's going to be so much fun this weekend doing the homework. You're just going to have so much fun. What do we get? Yeah, 108. Just plug in the limit. At this point, just plug in the limit, and you end up with 108. Nice. Nice. What's that?
That was bad.
Yeah. Let me recap. So the thing that helped us out on this was to expand that, and then we calculated, or then we were able to cancel the 216. Once we canceled the 216, you could factor out the h and cancel that. That's what really made the difference. If you're not keen on that, like I said, your alternative would be to take 6 plus h times 6 plus h times 6 plus h and multiply it out. I would suggest that you multiply it out by, starting out with 2 of these together, and then 6 plus h. That's going to give you 36 plus 6h plus 6h again plus h squared. Combine like terms. And then you're going to have to do, let's call it h squared plus 12h plus 36. Then you're going to have to distribute the 6, then distribute the h, and then collect all like terms. So that's, if you're not comfortable with Pascal's triangle, I get it. Maybe you haven't seen it before, or it's been a while. But one way or another, you're going to have to expand that binomial in order to get this. Please, it's not 100. It's not 218 or 216 plus h cubed. You can't do that. Any other comments or thoughts on this first one from example H? So let's do 2 more to finish this one up. Let's see. I'm going to skip the next one and move over to this one first. And again, I want to do a little just-in-time thing here for us. This time it's going to be reminder. A cubed plus b cubed. A cubed plus b cubed factors. And it's going to factor into the form of a plus b, a squared minus ab plus b squared. This doesn't factor any further. It is not equal to a plus b cubed. Don't try and take that shortcut. It just doesn't work. You will be making it easy for me to grade, if you know what I mean. A cubed minus b cubed factors pretty similarly, so I might as well go over both of them since you got the 1. Some of you who've had me before might remember what's coming up next. The formulas are pretty similar. You start out with what do you cube to get each of these? An a and a b. And then you take the first term and square it. Take this term and square it. Those are the end terms, but you need one more in the middle. And you get that by multiplying these 2 things together. The thing that you're going to have to remember next, which distinguishes these 2 formulas, is the sign. So, does anyone know why I'm writing this word soap in here? These 2 signs are the same. These are opposite. That one's always positive. So, minus, opposite would be a plus, always positive. Kind of says it right there. So that's our reminder. Let's now take a look at the limit as x approaches -2 of x plus 2 over x cubed plus 8. All right. Pahana, what do we do to start? What should we try? I don't think I've learned your name yet.
Olivia.
Olivia. Thanks, Olivia. What should we do to start?
Should we try to plug it in?
Yeah, perfect. Try plugging it in. So we'll do a little thought experiment. Try plugging it in. Einstein was famous for his thought experiments. He called them Gedanken experiments, literally thought experiments. In any case, -2 plus 2 is 0. -2 cubed is -8. Plus 8 is 0. So yeah, Lucas is like, oh man, when is it going to work out? There will be at least one on the test where all you have to do is plug in a limit. There will be one. So please don't ever forget about that. But, man, it doesn't work. What do we do? What can we do here? Lucas.
You make maybe like 2 cubes.
All right. Let's notice that that's 2 cubed. Yeah. Good observation. How does that help us out? Keep it going. You can factor it. In fact, that's the sum of cubes formula that's going to come out of this, right? So it's going to be an x and a 2. See if you can't fill in these last 3 there for yourself. What are those terms? Fill in the signs. Well, you're dividing both numerator and denominator by the same, so there is a 1. Good question. Okay. Gabrielle. How's this thing going to factor? So we got an x plus, yeah. All right, I guess I spilled the beans there. X plus 2. How about these last 3 here? What am I going to get there?
X
Mm-hmm.
plus minus 2x plus 4. So 2 is
Minus 2x plus 2 squared, which is 4. All right. So the nice thing here is that now these things are being multiplied, and I can cancel out the x plus 2. You know, I can show this a little bit more formally by splitting it up, etc. But there's one thing that's important when you cancel out that x plus 2. That doesn't leave a vacuum in the numerator, does it? What's left in the numerator?
1.
A 1. Limit as x approaches -2 of 1 over x squared minus 2x plus 4. Does that help us out? Cool. Keegan, what can we do now?
How you plug it in?
Yeah, plug in the limit. And you'll get 1/12. Nice. Now you can look on decimals, you can look on your graphing calculator, you can trace to the, but it's hard to actually pick up the exact number for some of these things by tracing. Sometimes you're gonna have to do this exactly. So, all right, looking good there. Let's do one more here, and then I'm going to ask you to think on one. Any comments or thoughts on this last one? This one?
You may talk about the H approaches 0.
Yeah, this one.
Yeah.
This one. So we want to look at that one. There's good news for you. Unlike the previous couple problems where I'm like, all right, you got to do this reminder, there's a reminder. There's not really a reminder we got to work on in this one. Not in the sense of the previous two. Limit as h approaches 0 of 3 plus h to the negative first power minus 3 to the negative first power over h. Let's remind ourselves of something here in a different way. And that is, suppose I had no idea. I mean, I don't know what the graph of this looks like, but I could look at this with a table and see if I can't at least come up with an estimate of what this limit might be. So I could put in 3 plus x parenthesis and then hit to the negative first power minus 3 to the negative first power over x. And let's just kind of take a quick look at it with the table. So do a table, let's get rid of those, and all right, I think I should have done Christian's trick here. Put math and then go to a decimal. There we go.
How did you just skip from the first to the last?
That's a kind of a cool trick. So if you're at the front of an expression, you want to get to the back, or vice versa. If you hit the second key and then the cursor, it'll take you all the way. So for instance, second here takes me to the front, second here takes me to the back. So it's a nice trick to get from one end of your expression to the other. All right, thanks for asking. Thanks for noticing. All right. So what would be some values that I could plug in to kind of look at the limit as h approaches 0 for this function?
-0.001.
Yeah. All right. We'll start out with negative 0.1 and negative 0.01 and get to Ethan's suggestion of negative 0.001. That's great. Someone finish this off for me. Let's see. Yes.
Well, the same thing, but in the positive.
Ah, perfect. Thank you. Same thing in the positive direction. Now, it might not be obvious what this decimal value is, what it represents as a fraction. But whatever it is, it looks like it's getting close to 0.11111. So, all right. So we'll kind of keep that in mind, but that's where it looks like it's headed. Now, as far as doing this one is concerned, do you remember what it means to have a negative exponent? What's that mean in terms of, yes?
You have to put a 1 over it.
Yeah. You're going to take its reciprocal. You're going to make that 1 a positive exponent, or excuse me, that negative 1 a positive 1. So it's going to look like this. Limit as h approaches 0 of 1 over 3 plus h minus 1 over 3 over h. And if you try plugging in h equals 0 either here or here, you're going to get a mess. You're just going to get 0 over 0 again, which is not so good. So we're going to have to do something. This is a reminder of some work that you did in college algebra with complex fractions. Now, what we like is we like to have one fraction here, not two. So there's a couple ways we could do that. Let's just do this. Let's get a common denominator in the numerator. Bring those two together. So, all right. Now, as far as the common denominator is concerned, both of these are separate denominators. So the LCD for the numerator uh, 3 plus h times 3. Need both terms there, both factors. So here's what I'll do. Let's take, let me write this down here. Limit as h approaches 0 I've got 1 over 3 plus h minus 1 over 3. In order to get the common denominator, what am I missing from this one that I have in my LCD? A 3. Now I can't just put in a 3, but I can multiply by a 1. So I'll multiply by 1 in the form of 3 over 3. What am I missing here? 3 plus h. So now it's a lot of messy algebra. But this is really what we need to get going on this one. So let's work on some of that messy algebra. So let's see, that's going to be the limit as h approaches 0 of 3 over 3 times 3 plus h minus 3 plus h over 3 times 3 plus h, still all over h. So all I did is effectively I got a common denominator for the numerator. And guess what? These have common denominators, so I can bring them together. All right. So let's see. That's going to be 3 times 3 plus h. And let's see if you can catch my mistake here. Ah, well done. You're subtracting this whole thing. So that means you've got to distribute the negative. So be careful with that. It's an easy place to make a mistake. There is a spot in this problem that you'd figure out that, wait a minute, something looks wrong, and maybe you can go back and figure it out. But when I distribute that negative, what's going to happen? What's going to be left? Let's kind of save ourselves a little bit of writing here. Yeah, I'll end up with a negative h. So I'll end up with negative h over 3 times 3 plus h over h, which at least is looking mercifully simpler, but we're not there yet. You still can't plug in h equals 0 because you'd end up with 0 over 0 again. But there is something we can do. Would it hurt at all if I thought of that as h over 1 in the denominator? Is that kind of the same thing? Yeah, same thing. So I've got a numerator and denominator. And here's the trick. One of them, I guess. What happens when you divide by a fraction?
Take the reciprocal and multiply.
Yep, you multiply by the reciprocal. So the limit, thank you, as h approaches 0 of negative h over 3 times 3 plus h times 1 over h. So that's my denominator here. This is my numerator here. Can you see daylight at the end of the tunnel? And it's not an oncoming train, so that's good. What are we going to finish up with here? Cancel out the h's. Hasta la vista. Wow.
What about that negative?
The negative doesn't cancel out, does it? But if you remember, our limit had a negative, didn't it? So it's going to be the limit as h approaches 0, negative 1 over 3 times 3 plus h Bob Real, what's that limit going to be?
What's the number going to be?
Yeah, what's the limit going to be? What's our best friend in terms of calculating limit? This is your go-to.
Or negative 1 over
Yeah, perfect. Plug in the limit. -1, 3 times 3, because that's a 0, is 9. And if you look at the decimal expansion of -1/9 on your calculator, it's the -0.11111 that we were seeing when we were looking at our table. So thank you and well done. Bless you. Whew. Wow. Looking good on that one. Now there's one that we didn't do here. Let's just talk our way through that one. Comments or thoughts on this one other than it was really cool and awesome? Yes?
I noticed when we put it in the graph, when we look at the graph, the points don't touch and they're like going opposite ways.
Let me take a look at the graph. Let's see. So I want this near, let's see, I want this near x equals 0, so let me set up a window like that. -2 to 2, and I'm just going to hit the zoom 0. I think they look like they're approaching the same thing from both directions. So, no, that looks, it's a good question. If you hit the trace key, move a little bit to the right, and then move back in, or move a little bit to the left and move back in, it's getting close to -0.111. Okay, no worries, no worries. The one we didn't do is one that you should be able to do. There was a trick that we used in doing something like this similar, or a similar problem to this one. What was it? Does anyone remember? What's the trick you're going to use on that one?
Switch it to the inverse, so -1, right?
I guess exactly what do you mean by the inverse?
Times h, or parentheses, 9 plus, and you can switch that. Oh. Who's talking?
Anyone help him out, John?
A plus b times a minus b.
Perfect. This is another one where you got to use the conjugate. This time it's in the numerator as opposed to the denominator, but it's going to be square root of 9 plus h plus 3 over square root of 9 plus h plus 3. Do yourself a favor. Just keep this one as 9 or h times this. After you square this out, you should get some cancellation and be able to eventually cancel the h on that one. So it's very much like what we did for example E. Whew. All right, let's put this one to rest.